Hello everyone. So today we're going to continue to talk about using implicit differentiation to find the derivatives of implicitly defined curves. And today we're going to be getting into slightly more complicated examples where we'll have to use the product rule and the chain rule together with this new idea of implicit differentiation. So I want to start by giving you a warm-up example. And then we'll go over it together and we can kind of use it as a reminder for what's the general procedure for implicit differentiation. So the warm-up example I would like you to do is find dy dx, or if you want, you can write it as y prime. But find dy dx for the relation e to the y is equal to y cubed plus x cubed. So please pause the video, try that for yourself just so that you remember how things work. I think that will help the rest of this video go more smoothly for you. Okay, so how does this work? So the general idea is that we're kind of changing our point of view for how we're taking derivatives, and we're basically kind of taking the derivatives of both sides of an equation. So we're going to start by taking the derivative with respect to x. And I talked about this a little bit last time, but I just want to say it again. So the thing that I think is sort of most important to understand when you're doing implicit differentiation is that you're treating x and y differently, right? Like the way that it goes when you take the derivative of x is different from how it goes when you take the derivative of y. And the reason for that is that we're thinking of x as our input variable. We're thinking about it as the independent variable, because we're taking the derivative with respect to x. That's what d dx means. We're not going to be doing this in this class, but you could, if you wanted to, take the derivative with respect to y instead, and then things would go differently. But the important thing is that because we're taking the derivative with respect to x, that basically allows us to take the derivatives of the parts that are just x's, quote unquote, normally, and then it's just when we get to the y's that we have that extra step that we'll have to do. So what does that extra step look like? Well, basically, you're thinking of this as the chain rule. So, just to give kind of a side example, if you were taking the derivative of, let's say, e to the sine of x, you would have to use the chain rule, right? So you would say your outer derivative would be e to the sine of x, because e to a power always stays the same in the kind of first part of the derivative, and then you would multiply that by the derivative of the exponent, because that is your inner function. And so it's really the same idea here. It's just that y isn't any kind of explicit function of x, but we're kind of considering it to be a function of x in the way that we take the derivative. So it's like, I don't know, you think of y as being like some mystery function that you don't know what it is, and so when you take its derivative, you just have to kind of write y prime as a placeholder. So this derivative ends up being e to the y times y prime. So this is our outer derivative, and this is our inner derivative. And then on the right-hand side, we get, so the derivative of y cubed, again, we have to do this chain rule thing, where we're first going to take the outside derivative, so we're going to do 3y squared, and then we have to multiply that by y prime because that's the inside derivative. And then when we get to anything that is only an x, you're only a function of x, then we don't have to worry about any of the extra stuff, and we just kind of take the derivative normally. So we get 3x squared. So the next step is basically we're trying to solve for y prime, and so we want to rearrange this equation to help us to isolate y prime. And so that means that anything that contains a y prime in it, we want to move that to one side, and anything that doesn't, we want to move that to the other side. So in this case, let's subtract this term from both sides. So we'll end up with e to the y times y prime minus 3y squared times y prime is equal to 3x squared. And so now we can factor out a y prime from everything on the left-hand side. So we end up with e to the y minus 3y squared. And then we can divide both sides to allow us to isolate the y prime. So we end up with 3x squared over e to the y minus 3y squared. And so what should happen is that your derivative, y prime, is going to have a blend of both x's and y's. And we talked a little bit about why that is last time, but basically it's because these curves that we're working with are generally not going to be functions. It's not enough information to just plug in an x value because there are going to be multiple points at a given x value. So you need to plug in both an x and a y value to know what the slope of the tangent line is at that part of the graph. So I want to, for each of these, show you what the graph looks like, just because, like I said last time, I think they're kind of interesting. So that's what the graph of e to the y is equal to y cubed over x cubed looks like. Okay, so let's do another. So we're going to now get into some more complicated examples. And so we're going to do, let's see, 1, 2, 3 to 4 examples. So, at any point, if you feel like you're getting the hang of it, I would definitely recommend pausing the video and trying it yourself and then coming back and seeing how it went. I would stick through to the end though, because the last example we're going to do, I'm going to bring up a trick that will kind of make things a lot faster for certain types of problems. So I would recommend sticking through to the end, even if you feel like you're getting pretty comfortable with some of these other examples. Okay, so basically today, oops, things are all going crazy. As I said, the main issue is that now we're going to be looking at how using how the product rule and chain rule kind of interact with implicit differentiation. And I know that the chain rule kind of is related anyway to implicit differentiation, but you'll see what I mean. I mean, we'll basically be looking at some examples where you have something like sine of y squared. That would be an example of where you have to use the chain rule kind of aside from the implicit differentiation part. So using the product rule and, oops, chain rule with implicit differentiation. Differentiation, yes. Okay. So basically, it's going to be pretty much the same deal as what we did before. The main thing I just want to draw your attention to is that you have to really keep track of when is it that you're taking the derivative of the part containing the y, because that's the only place where you're going to be multiplying by y prime. So let's look at an example, and I think that will kind of make it clear what I mean by that. Okay, so let's say we wanted to find y prime or dy dx for the relation x cubed plus y cubed is equal to 6 times x times y. So what's different about this one is that now we have a product rule going on the right side. So we'll see what happens with that basically when we get there. So we take the derivative of both sides. So x cubed plus y cubed, and then we're taking the derivative of 6xy. Okay, so the left-hand side is actually very similar. It's like the same as the right-hand side in our last example. So we know that we're going to get 3x squared for the first part, and then we're going to get 3y squared times y prime. Okay, so what about on this right-hand side? Well, this is a product, right? And so let's think of this as being the product of 6x and y. And so we're going to use the product rule basically the exact same way that we always do. So how does the product rule work? Well, I'm going to write out the steps kind of in that using that prime notation. So the way the product rule works is that first we're going to take the derivative of 6x. So we're going to take the derivative of 6x, and we're then going to multiply that with just y. Right? Because you're doing the derivative of the first function times the second function. Then we're going to take the derivative of the second function and multiply it with the first function. So let me fill out this left hand here. So what's the derivative of 6x? It's just 6, right? Derivative of, when you're just dealing with x, it's just kind of the normal derivative. So we just get 6. And then we have 6 times y. Notice I am not multiplying by y prime in this stage, and the reason that there's no y prime here is because in this part of the product rule, we were not taking the derivative of y. So that's what I mean when I say you really have to keep track of, like, when you get to a more complicated expression, there will be part of the expression where you're taking the derivative of y and part where you're not. And so in this part, we are not taking the derivative of y, so there's no y prime involved. So then the next part, well, now we are taking the derivative of y. So what's the derivative of just y on its own? Well, it's basically just 1 times y prime, right? Because, like, let's say if it was instead, y squared, well, then the derivative would be 2y times y prime, right? You're kind of taking the derivative of y squared normally and then multiplying it by y prime. So if your function is just y, the derivative is just going to be 1 times y prime. So it's just y prime. So we get y prime times 6x. So it's really just using the chain rule normally and just kind of keeping track of when you are and are not taking the derivative of y and only multiplying by y prime in the exact moment where you're taking the derivative of the part that involves y. Okay, so what do we have here? We have 3x squared plus 3y squared times y prime. And let's actually start to, let me erase this because I got ahead of myself. Let's move all the y primes to the same side. So I'm going to subtract 3x squared from both sides, and I'm going to subtract y prime times 6x from both sides. So we're going to be left with 3y squared times y prime minus 6x times y prime is equal to 6y minus 3x squared. And so we get y prime, and factor that out, we have y prime times 3y squared minus 6x is equal to 6y minus 3x squared. And so this gives us y prime is equal to 6y minus 3x squared over 3y squared minus 6x. Which has some kind of nice symmetry to it, right? Like the x's and y's are just kind of like flipped from each other in a way. So let me show you what this graph looks like. So this one is called the folium of Descartes. I guess it's famous for some reason. I'm not exactly sure, but Descartes is a very famous mathematician. But yeah, that's it. And you can see the graph is pretty symmetric, and so that's kind of reflected in the fact that the derivative has some symmetry about what goes on when you plug in different x and y values. Okay. So that was just using basically the product rule in a fairly straightforward way. So the next one we're going to do is going to involve the chain rule and also the product rule. So this one's going to be a little bit tricky for sure, but we'll stick with it. And I think the main thing that I think can be kind of stressful for a lot of students with these problems is that somehow just having the x's and the y's, it just feels like a lot. It feels kind of messy, right? There's like a lot of different letters and everything going on, but really the logic of it is the same as everything we've been doing. It's really just that it kind of looks more confusing because there's more different characters involved. Okay, so we have sine of x times y is equal to e to the y plus x. So let's find y prime. Okay, so we're going to take the derivative with respect to x of both sides. And the left side is definitely the side that is going to give us more of an issue, right? We kind of know how to take the derivative of everything on the right-hand side. So how's this going to go on the left-hand side? Well, we know that we're going to have to use the chain rule, right? Because it's not just sine of x, it's not just sine of y, it's sine of x times y. And so it tells us we're going to use the chain rule. And so this is really, I think, the point where if you're always writing down your inner and your outer function and everything like that when you're doing the chain rule, I think you're going to have a kind of a hard time doing the chain rule here because it would just get kind of confusing what to even write down because these are not just functions of x, they're functions of x and y. So I think being able to have this viewpoint of kind of taking the outer derivative and leaving the inside the same, and then multiplying that by the derivative of the inside function. I think that's kind of the better way to look at this. So let's start by doing the outer derivative. So we're going to take the derivative of sine, and then we're going to leave our input the same. So the derivative of sine of something is cosine. And so we have cosine of x times y. So we're taking the derivative only of the outside and leaving the inside alone. Then we have to multiply by the derivative of the inside function. So how do we take that derivative? Well, it's basically going to be just like the one that we did right here. It's going to be very similar to this derivative, right? It's just a product of x and y. So what is that derivative going to be? Well, first we're going to take the derivative of x, and the derivative of x is just 1. And then we're going to multiply that with y. Again, we're not writing y prime because we're not taking the derivative of y in that part, right? The first part of the product rule, you're just taking the derivative of the first thing that's being multiplied. But then in the next part, then we take the derivative of y, and that gives us y prime. And then we leave x as it is, and we don't take the derivative of x. So just kind of the regular product rule. Yeah. So basically this is just a chain rule with a product rule within it. And again, maybe just to emphasize again, we never multiplied like by y prime here or anything. Like we didn't multiply by y prime until we got to the very moment where we're taking the derivative of y. Because all the other parts, when you do the outside part of the chain rule, you're not really messing with the inside stuff, right? You're just taking the kind of outer derivative. And so y prime just didn't really come up until the very moment where we got into the second part of the product rule. Okay, so next here we have the derivative of e to the y. So we saw that one in our warm-up example. That one is going to be e to the y times y prime. And then the derivative of x, we know that that is just 1. Okay, so now we're going to distribute this. And so this is where things will start to look kind of crazy and messy, but just believe that like if you know how to simplify an algebraic expression, it's really just the same thing. It's just that it is going to look a little bit crazier because there's more different letters going on. So we're going to multiply, we're going to distribute in like this. So we're going to get y times cosine of xy plus y prime x times cosine of xy is equal to y prime e to the y plus 1. And by the way, maybe let me just say one more thing, side note, is that I think the most common place I see students make mistakes on a question like this is that students will forget the parentheses here. And what ends up happening is that then you'll just have this y prime x part kind of floating by itself when really it should be getting multiplied to cosine of x times y. So make sure whenever you're using the product rule, or sorry, the chain rule together with the product rule, whether it's in this context or kind of regular derivatives, just make sure you put parentheses about around whatever you're multiplying by. Okay, so next step is getting the y prime parts by themselves and putting everything else on the other side. So that will give us y prime x times cosine of xy minus y prime e to the y is equal to 1 minus y times cosine of xy. So now we want to multiply, or sorry, factor out a y prime. So we have x times cosine of xy minus e to the y is equal to 1 minus y times cosine of xy. And so solving for y prime, we get y prime is equal to 1 minus y times cosine of xy divided by x times cosine of xy minus e to the y. So, and we'll do an example like this at the end, but if you were trying to find the slope of the tangent line at a specific point, you would just plug in x and y, right? I just want to make sure everyone remembers how, what's the whole point of y prime? It just tells us the slope of the tangent line at different points. So let's also look at the graph of this one. So that was this one, right? Sine of xy is equal to e to the y plus x. So kind of interesting shape, I think. Anyway. All right, so we'll do one more that's just finding the derivative, and then the last example we'll do is going to be finding an equation of a tangent line, and that's where we'll see that there's kind of a little shortcut that we can do. So let's now do find y prime for y times e to the x plus x times e to the y is equal to e to the x times y. Okay, so you know the drill by now. We're taking the derivative with respect to x of both sides. And in this case, we're not off the hook on any of these, right? All of these are going to involve some kind of product or chain rule. So let's start with the first part. So the first part we can think of as being the product of y and e to the x. So we're going to apply the product rule. Again, just really making sure that we're only multiplying by y prime at kind of the correct part. So the product rule, so let me just highlight this to remind us that we're doing the product rule. So the product rule says that you take the derivative of the first thing. So the first thing we're going to do is y prime, right? We saw in a previous example, that's the derivative of y. And then we're multiplying that with e to the x. And then we're going to take the derivative of e to the x, which is just e to the x, and multiply that with y. So just using the product rule as you normally would. The next part, again, is the product rule, but it's things are kind of flipped around. So now we're going to start by taking the derivative of x. So the derivative of x is just 1. And then we just multiply that with e to the y. We're not going to do any y prime business because at this step, we're not taking the derivative of e to the y. We're just taking the derivative of x. And then the next part of the product rule is where we do take the derivative of e to the y. So we know that the derivative of e to the y is e to the y times y prime, because e to the y is the outer derivative and y prime is the inner derivative. And then we're supposed to multiply that with x. So first part was our first product rule. This is product rule number 1, and this is product rule number 2. Maybe I'll write that down, because it all kind of looks the same, so I want to make sure you can tell where everything came from. Okay, so the last one is going to be kind of similar to what we did on this example. So in this example, we had to do sine of x times y, and so we had this chain rule with a product rule inside, and so we're going to have to do that in this case as well. So when we're taking the derivative of e to a power, the first part of the derivative is just going to be e to that same power. So it's kind of like if we were doing the derivative of like e to the sine of x, right? We would just say e to the sine of x. Then we want to multiply by the derivative of the exponent, since that's our inside function. And so in this case, the inside function is x times y. So what's the derivative of x times y? Well, first we would do the derivative of x, which is 1, and multiply that with y without doing any y prime. And then in the second part, we take the derivative of y, which is y prime, and we multiply that by x. So we're just using the product rule on that part because that was our inner function. Okay, so now we can kind of simplify everything. So we have y prime e to the x plus e to the xy plus e to the y, a lot of terms in this one, plus y prime e to the y x, maybe I'll put the x beforehand, is equal to, and let's distribute on this side. And again, make sure you put those parentheses. If you didn't put the parentheses on the right-hand side, you would not get this correct. So when we distribute this, we get y times e to the xy plus y prime x e to the xy. Okay, so let's gather up everything that has a y prime in it. So let's see, that would be this, this, and this. And then we'll put everything else on the other side. So we have y prime e to the x minus, or sorry, that one's already on this side. Never mind. This one's already on the side, so let's leave it here. Plus y prime x e to the y. And then let's subtract this one to the other side. So then we'll have minus y prime x e to the xy. And then on the right-hand side, we have y e to the xy, and then we'll subtract over this and this. So minus e to the xy plus e to the y. Okay. Finally, we can factor out y prime, and so we have e to the x plus x e to the y minus x e to the xy. And same stuff still on the right-hand side. I hope I didn't make any mistakes. I feel like everything kind of looks the same in this problem, so definitely easy to get confused on this one. So if we divide everything, we'll get y e to the xy minus, I'll write it as y e to the x plus e to the y divided by e to the x plus x e to the y minus x e to the xy. And again, I think this is kind of a satisfying derivative. Like if you look at it, it's very symmetric. Like everything that appears, kind of the opposite of it appears, right? We have y e to the xy, and then we have x e to the xy. And then we have x e to the y, and we have y e to the x. And then the signs are all flipped too. So it's just, or at least some of the signs are flipped. So kind of interesting. So let's take a gander at this graph. This one actually is not as interesting as I expected it to be. Oops. So it just looks like this. Kind of interesting how it has these two kind of nesting pieces, but not as crazy as some of the other ones. All right, so we're going to do one more example. And in this next one, like I said, there's going to be kind of a new trick that comes up. So in this example, we're not going to actually find dy dx. We're just going to find the equation of a tangent line. So find the equation of the line tangent to, so our relation is sine of x plus y is equal to y times cosine of x. And we're going to be finding the equation of that tangent line at the point pi over 2, pi over 2. Okay, so the part that is going to be kind of the trick here is that we're going to start by taking the derivative, but we're going to plug in our point kind of sooner than you might think. And that's actually going to make things a lot easier to solve. So keep an eye out for that. So the first step we're going to do is we're going to basically take the derivative so that we are able to find the slope. So we're going to take the derivative of the left-hand side, and then we're going to take the derivative of the right-hand side. Okay, so what's going on this left-hand side? Well, we're going to have a chain rule, right? Because we're not just taking sine of y or sine of x, we're taking sine of something else, in this case, x plus y. And so what is the chain rule going to look like? So first we'll take the derivative of the outside function. So the sine part is going to give us cosine of x plus y, right? Because the derivative of sine is cosine. So that's the outer part of the derivative. Again, there's no y prime appearing because we're not really messing with the inside at that part. So next part is multiplying by the derivative of the inside function. So now we just have to take the derivative of x plus y. So we don't have to use the product rule or anything else, right? It's just a sum of two things. So the derivative of x is just 1, and the derivative of y is y prime. And really remember to put those parentheses. And then on the right-hand side, we have to use the product rule, right? So we start by taking the derivative of y, and that's equal to y prime. and then we leave cosine of x as is. And then in the second step of the product rule, then we take the derivative of cosine of x, which is negative sine of x, and we multiply that with y. So let me just clean this up a little bit. But we're not actually going to solve this for y prime yet. And I'll explain why in a second. That plus minus is bothering me, so I'm just going to write that a little differently. And let me put the y first too. Okay, so this is the key step that's going to be different than on the other ones. So this method is not going to work if you're supposed to find dy dx. If the question specifically asks you to find dy dx or find y prime, so basically like all the other examples we did today, you can't do what we're about to do. But if the question is specifically only asking you for the slope at a certain point or for the tangent line at a certain point, you can plug in the point after taking the derivative, but before solving for y prime. So let me try to kind of summarize that in words. So if you are not asked for a general formula, and so this is going to come up on some of the homework questions for sure. So if you're not asked for a general formula for y prime or dy dx, you can plug in the point where, I'll just say the point, you know what I mean, right? The point where you're trying to find the slope. So you can plug in the point where you're trying to find the slope after, it's really important you plug it in after taking the derivative. Because if you plug it in before, then you'll just have a bunch of numbers and you'll have nothing to take the derivative of. But if you plug it in after taking the derivative, but before solving for y prime, so why would you do this? Well, basically, what makes this step, like, personally, if I look at this, I kind of look at this and say that doesn't really look like something I'm dying to solve for y prime, right? It's not going to be that bad, but like the algebra is a little annoying. There's a lot of stuff going on. And the reason that is because we have an x, we have a y, we have y prime, we have all this other stuff. We have 3 different variables in this equation. So if we plug in our number, we'll be left with only one variable, right? If we plug in the point, so the point that we were looking at here was pi over 2. If we plug that point in, then we'll only have numbers and y prime. And so that will just make solving for y prime be a smoother experience. So we're just going to plug in every place where we see an x or a y, we're going to replace it with pi over 2. So the original function was, or expression was cosine of x plus y, so that becomes cosine of pi over 2 plus pi over 2 times 1 plus y prime. So we can't plug anything for y prime. We don't know what y prime is. So that has to stay. But anything that is just an x or a y, we can replace that with pi over 2. So y is pi over 2. Okay, so why is this especially helpful? Well, sine and cosine of pi over 2, and here we're going to get pi, right? Pi over 2 plus pi over 2 is pi. So I'll just rewrite this whole thing. Cosine of pi. So those are all really easy ones to evaluate on the unit circle because they are just going to either be 1, 0, negative 1. Like they're not ones where you have to remember all of the different, sorry, I'm getting distracted trying to talk and write at the same time. They're not ones where you have to remember like, oh, root 3 over 2, 1/2, things like that. It's just looking at the unit circle in a very simple way. So we have 2 different angles. So one of them is pi. So pi is going to be over here. So this is an angle of pi. And so this point here has coordinates of -1, 0, right? Just like looking at the unit circle. And so that tells us that cosine of pi is -1. So we're left with -1 times 1 plus y prime is equal to y prime times, so pi over 2 is going to be this angle here. So this is pi over 2. And that has coordinates 0, 1. So cosine of pi over 2 is just 0. And so that part is actually going to go away. And then here we have pi over 2 times sine of pi over 2. So sine of pi over 2 is 1. And now we can go in and solve this. So if we distribute this -1, we end up with -1 minus y prime is equal to, this part goes away, and then we just have negative pi over 2. And personally, I just want to divide everything by -1 or multiply everything by -1 because that just makes my brain handle this more easily. So if we divide or multiply everything by -1, we end up with this. And so this tells us that y prime is equal to pi over 2 minus 1. So this is going to be the slope of the tangent line that we're looking for, right? We're looking for the slope of the tangent line at that point. And so now to finish this off, we just have to put our equation in point slope form. And in this case, because our slope is kind of this funny number, but we want to really leave it in exact form, we're just going to leave it in point slope form, because if you put it in slope intercept, it would just get kind of, the numbers, or it would just not look as simple as leaving it in point slope form. So we can write our equation in point slope form. So equation of the tangent line is going to be y minus pi over 2, right? Because that was our y coordinate of our point, is equal to, and then our slope is pi over 2 minus 1. And then we have x minus pi over 2 as well. So let's go scope this out real quick on Desmos. So here is the graph of sine of x plus y is equal to y times cosine of x. And so the point we were focusing on was this point here, pi over 2 comma pi over 2. And here is our crazy looking line equation, but it looks like that is the correct tangent line. All right, so that is it for today. There's a worksheet with some more examples of these slightly more complicated implicit differentiation problems. And yeah, tomorrow we'll see how implicit differentiation can be used to help us figure out some new derivative rules. And that's what we'll be talking about, in tomorrow's video. All right, I will see you then.